Hello, I am Pranav Patel. I'm privileged to serve Meditech Safe, a healthcare cybersecurity brand, and Resilient, an industrial cybersecurity brand. At Resilient, we enable digital transformation to help organizations realize value in terms of productivity, customer experience, and quality by providing next-generation cybersecurity solutions focused on enterprise cybersecurity, IoT and operations technology cybersecurity, product cybersecurity, supply chain cybersecurity, and training and awareness. You can learn more about the company and the topic by visiting our websites, resilient.co and meditechsafe.com, or connecting with one of my colleagues directly. I personally wanted to get engaged in developing a course because sharing learnings and ideas that make our world a better place is a passion of mine. We've entered the era of digital transformation. For example, Boston Consulting Group estimates that factory of the future with more connectivity and automation will deliver anywhere between 15 to 40% of conversion cost productivity. That's a significant value to be had. The biggest hindrance to that vision is cybersecurity. A cost-productive approach to operational technology or IoT cybersecurity will help maximize net gain from digital transformation. It will make the world more productive and secure. Before we get on to the topic, let's calibrate ourselves. Answer this question to yourself. You can even write it down on a piece of paper. How do you rate your level of confidence with regards to cybersecurity in your organization? No confidence, somewhat confident, increasing every day, above average, or very confident. You can track in your mind how you feel about this question over time during this course. Here are some examples from the last year. An iconic company from virtually every category has been breached. In just the last couple of months, we have heard about a leading cosmetic group, Pierre Fabre, an IoT manufacturer, Sierra Wireless, an electronics manufacturing services company, Astil Flash, being breached. All of these have faced production disruptions. XFab, a semiconductor manufacturer, also faced ransomware late last year. I remember as a kid asking my father for help with my chemistry class once. I asked him if he can help me with the reaction sequence to get to benzanthrone from benzene. He turned around and said, "Son, I'm a chemical engineer, not a chemist." That was an important learning in that brief response. As engineers, we focus on practical solutions to problems. A solution requires a broader perspective. It requires understanding of what's possible from a given set of technologies, determining concrete steps of implementation, ensuring effectiveness of the solution while having the lowest cost and highest reliability. That's the philosophy we'll take in this session, a systems engineering approach to cybersecurity. In other words, we'll focus on a solution rather than a specific tool or a technology. We often miss to recognize the difference between the two. For example, in this automotive plant, a problem statement is that this robotic arm needs repair. It has caused either a production line outage or poor quality output. The solution to this problem is not just a tool. The tool, as shown in the figure, can support the solution by improving speed or accuracy of diagnosis and maybe repair. But solution involves coordinating multiple items, such as skills of an engineer or a technician, process of diagnosis or repair, upstream or downstream activities such as planning a downtime of the equipment or testing the system performance after the repair. We will devote our focus on arriving to a solution of this broader OT cybersecurity problem, not just a tool. For starters, cybersecurity is challenging because it requires us to deal with a complex system. By system, I mean the entire entity, which includes all employees, various processes, many systems and technologies, and a complex interaction among them. There are multiple inputs and outputs. Cybersecurity efforts include three main elements: risk management, which is all about prevention, detection of anomaly when a breach takes place, and response and recovery back to the desired steady state. Organizations predominantly focus on detection and response from a closed loop system perspective using a SOC and incident response plan. That is the priority for IT cybersecurity. Preventing a disruption of operations is critical, though. It is certainly the case for OT, operations technology. In many closed loop systems, we have a good understanding of variables, and we tend to control them well. In case of cybersecurity, we have very many uncontrolled and unknown variables. From a risk management perspective, if each input variable is managed via closed loop system, it can allow a better control to the main system, which is the entity of concern here. We know that uncontrolled and unknown variables translate to difficulties in overall system control. At the same time, more interconnectivity in the system, as expected with proliferation IoT, would mean longer response time to achieve steady state recovery if a breach were to take place. Unfortunately, the variables span across the whole value chain. No wonder cyber breaches in manufacturing have skyrocketed. As we see here, it is just not external actors that need to be managed, but also internal and partners that we should be concerned about. In fact, each one of these categories is a sizable contributor. So let's understand these variables. We'll look at a handful of breaches in detail to get a better context for the solution that we want to propose. All of us have likely heard about the SolarWinds attack. It is interesting to see how this supply chain attack took place. It started around September 19, when attackers gained access to SolarWinds build server. The build server is where developers contribute multiple modules to build a software application. The SolarWinds development team shared the password SolarWinds123 to access this build server for months. Now, it wasn't too difficult for the bad guys to try. They introduced a malware called Sunspot to the build server. This malware watched for build commands so that another malware named Sunburst can be introduced to the Orion application. The application update was pushed to all of their customers, including many federal agencies. It went undetected because it came from a trusted source. Sunburst exported data to the command and control servers. When it found an important asset, it was replaced by Teardrop. Now, this speaks to the need for strengthening IT operational and sourcing processes, isn't it? Last year, a US natural gas pipeline was forced into a shutdown. In this case, an employee fell for a malicious email. The malware infected that IT network before spreading to the OT network. It blocked systems from working properly and obtaining data from lower level operational devices. The networks weren't segmented or segmented well. Very similar to the pipeline example, the US maritime base faced a ransomware incident last year. In this phishing attack, the malware propagated to the industrial control systems that monitored and controlled cargo transfer, cameras, door accesses, and more. And this caused a forced shutdown for 30 hours. The ransom demand was for 14 million. While from the surface, it may seem like just another phishing attack. There were likely many other vulnerabilities at play though. Was the network not segmented? Were there configuration errors? Etc. Let's look at another example. This is one more supply chain attack. The cybersecurity camera company Verkada's super admin credentials were available on internet. How did that happen? Answer to this question could be very revealing. The super admin credentials allowed root access to cameras. The bad actors were able to access the internal networks of Verkada's customers, such as Tesla, Cloudflare, Halifax, and others. The incident raised many security concerns. In this example, a Midwest-based hospital had outsourced the janitorial services to an external party. It isn't unusual for companies to outsource facility management services, as you know. This cleaning crew member cleans the facility every day. One day he noticed a computer console that is not password protected and connected to the internet. He thought it was okay for him to check his personal emails. Well, he became victim of a phishing attack that infected the computer. Apparently, this hospital did not renew the key post-warranty period for this CT system. The computer console controlled the CT system. This ransomware attack infected the CT system and the network, demanding a ransom. You might have heard about the Ardsmar water facility incident this year. In this case, all computers had connections to the SCADA system. The computers also had TeamViewer for remote access. The password for this remote access was openly shared. There was no firewall protection. Apparently, the remote access credentials somehow ended up in the hands of the bad guys. The hackers gained control of the water treatment system and increased the eye level by 100 times. This could have been a deadly incident. Let's look at the last example to see the impact. TSMC is one of the largest semiconductor companies. It faced a disruptive cyber attack a couple of years ago. In a foundry, there are many systems like the one shown in the figure, each one with multiple integrated computers and operating systems. In this case, a system needed a software to be installed by a technician. Apparently, this software was infected by WannaCry malware. When it was installed to this Windows 7 based system and the system went live, this malware started to spread across multiple plants, causing shutdowns. We should ask ourselves how often integrity of a system is tested for cybersecurity after a maintenance cycle. How are the network configured to contain the impact? Hancock Hospital in Indiana faced a similar ransomware incident, and equipment was being remotely monitored by the manufacturer's services team. The remote engineer had allowed the remote access credential to be stored in the browser. The hackers were somehow able to obtain the credentials from the cookies and gain remote access to the hospital network. So when I discussed some of these examples in a chemical engineering conference recently, a gentleman asked me a question. He said, This thing should be easily managed by processes, policies, and tools. Shouldn't we be able to get to 100% risk management? I provided an analogy of chronic disease such as diabetes and hypertension. Your primary care physician would often say, manage your diet, exercise, sleep well, and reduce stress. But how often are we able to comply to that? So achieving maturity is difficult when there are many scenarios of attacks and vulnerabilities. We call them uncontrolled and unknown variables here in our earlier chart. Now let's answer a few questions that can guide us to an optimal solution. First, let's revisit our original question. How prepared do you feel your organization is to address cybersecurity risk? You just have to answer that question in your mind. What boundaries are considered in your current solution? For example, are your efforts limited to certain networks such as IT networks or systems? Do you consider only the external actors? Do you look at only network-based attacks? Are your efforts limited to certain functions such as IT or security? Answers should help you highlight the gaps in scope. Is prevention more important to you, or detection only sufficient in your context? Answer would vary based on your company culture, business model, and risk appetite. For example, some companies have stronger preventive maintenance programs than others. Some only perform maintenance reactively. So culture matters, business model matters. Now we're ready to look at the solution approach. As we said, it is better to identify optimal boundaries for the solution based on risk, which depends on the business model. No organization has unlimited resources to devote to cybersecurity. In absence of understanding the risk, one might overinvest in one area where risk is lower, or underinvest where risk might be higher. It will lead to either capital inefficiency or unaddressed risk. In this figure, we have a general view of an OT network. As you see, there are bugs that can enter from outside, and there are bugs inside. The bugs represent origination point or points for attack vectors. There are many tools available to manage cybersecurity. In fact, some of the network level controls, such as perimeter controls, including firewalls and access management, may already be in your place. You might also have intrusion detection and a vibrant SOC. SOC is Security Operations Center. You probably segment your network well. These are some of the network level strategies. As we saw in the examples, many things could go wrong at an operational level. So tracking assets, vulnerabilities, and status of risk mitigation is very important. Having a robust incident response and recovery mechanism is a necessity nowadays. The risk-based approach would recommend identifying how much risk can be reduced by each one of the strategies outlined here. This means that we have to first understand the value of each strategy or technology and its ability to contribute to the risk reduction. Each strategy or solution element can be evaluated by some of these parameters. Effectiveness. Does this solution retire the expected level of risk? Efficiency. Is the total cost of ownership low enough for the risk needing to be addressed? Adaptability. An operating environment may change often. Can this solution be easily adapted to the new realities? Would there be a big cost of change or cost for change? Sustainability. Can this solution work in all situations? Let's now evaluate the most advanced solutions available. IoT and operations technology, or OT cybersecurity, faces many constraints, as you know. For example, active scanning to identify devices and vulnerabilities is not always feasible. It may shut down devices or put them into a reboot loop. Adding agents may impact an asset's performance adversely. User-centered access management to each system may be operationally difficult to implement or could be counterproductive. So considering such constraints, vendors now promote these three technologies as highlighted in the chart. They require access to network nodes. With that, they enable passive scanning for asset discovery and profiling of the asset for vulnerability management. The goal is to identify all assets, track them over time, and track the needs for patches quickly and efficiently. The performance is improved with the ability of performing deep packet inspection at layer 7, where all packet or each packet is separately evaluated. This is feasible because industrial protocols such as Ethernet IP is unencrypted. Monitoring for anomalous behavior at each node using artificial intelligence is the second tool. Goal is to detect intrusions or threats quickly before much, if any, damage takes place. The performance is expected to be better if one can inspect each packet with DPI, that's deep packet inspection. If you identify an alert of an intrusion and link that directly with the automated network policy manager to either isolate the system or revoke certain accesses, you can save or contain the damage. And that's the goal behind using smart or advanced intrusion detection or intrusion prevention systems. The third, driving segmentation to further granularity all the way up to microsegmentation level. This could, in theory, allow one to put each system in a separate cabinet, so to speak. The segmentation policies can be linked to intrusion detection system, as we just discussed. The latter two are becoming more prominent in the IT side of the world. The DPI is more difficult in IT side because the packets are mostly encrypted and OEMs would typically not provide the encryption keys. It is important to understand the trade-offs involving these technologies before implementing them. We can use the solution evaluation grid to assess the merits of these technologies. Let's start with the first one, asset discovery and profiling via DPI. There are benefits to using this technology. It offers the benefits of speed and cost in discovering assets and profiling them. You can track assets and vulnerabilities. All you need is a good network coverage, and mostly everything else can be automated. There are, some of the questions that one should ask though. For example, will all your network connectable devices be discovered? Many assets can be in a peer-to-peer configurations and may sit behind workstations, so to speak. Many assets may communicate via proprietary protocols. It is difficult to discover and profile such assets. If they are not profiled, how else the risk stemming from these assets will be addressed? How accurate is the asset information? Many connectable systems have multiple MAC addresses. Many times OEMs do not include sufficient information in the packet or the header. They may include high-level system type, but not necessarily the model level information. You may not be able to get operating system version level or patch level. So do you need an alternative method to validate the information? What is the cost of that? How comprehensive is the asset information for risk management. For example, while scans may provide some operating system level information, you will still not have information about other software bill of materials. Scanning will not fully reveal asset or system configurations. What if system has been through upgrades? Would you need another method to supplement this effort? What is the cost of that? Is there an asset authentication risk? There is a possibility of spoofing. A malicious device or an asset can be whitelisted based on some spoofed packet level information if there is no validation mechanism. What would happen if OEMs started to encrypt the data in future? All manufacturers are looking to increase security of their products. Would that action reduce the value of this method and installation over time? You can assess the applicability of this technology in your environment using the evaluation grid parameters and asking right questions and evaluating the answers. The second one, anomaly detection using artificial intelligence and automated policy actions via integration. Value here is in its ability to deliver early detection of an intrusion or a threat. The highlighted questions here can help you evaluate applicability of this technology in your environment. So let's look at some of them. How many false positives are expected? Typical IDS generates many alerts, and studies indicate that 80% of them tend to be false positive. Because OTSs operate relatively consistently, the false alerts rate can be lower. At the same time, network complexities and where the detection sensor is placed can also impact number of false alarms. Now, one way to manage false positives is to have an analyst in the loop to triage and validate the alerts. What would be the cost of having OT system specialist as analyst in the loop for triaging the alerts? Would you have to take system offline to evaluate each alert? What would be the cost of having a specialist for each Unix system or downtime impact? How would accuracy of detection change if access to the packet level information is not available anymore? DPI may not be feasible if data are encrypted by the OEMs. Would OEMs provide encryption keys? What is the risk of having encryption keys? If there are many false positives, the team at ground can start to ignore some of the alerts. It happened in the case of Target breach, if you remember. Are there any legal liabilities associated with failure to act? Let's say in a safety incident. Again, the evaluation grid can help you assess the applicability of this technology in your environment. The third one, granular segmentation. Better segmentation can certainly help in containing impact. It also provides increased protection against specific target attacks. Let's look at some of the questions to determine a strategy involving segmentation. What is the network performance impact for granular segmentation? Segmentation performed at the session layer, which happens in the case of firewalls, or at application layer, which allows microsegmentation, would have impact on the network performance and will increase the management burden, by the way. When devices or assets are added or moved around, the policies must be managed. What would be the cost, if any, to manage policy by having dedicated personnel? What is the risk of not managing policies over time? So one must go through all pros and cons to determine if a technology or solution is applicable and would yield good result in that environment. Considering a real example of an OT system could help see the complexity of OT cybersecurity. Here's a typical system of systems that can be found in a machine shop. A scanning operation will not discover the calibration tool that is connected to the lathe via Bluetooth or USB. Hence, the vulnerabilities associated with their operations have to be identified and managed separately. The lathe has multiple systems within that, such as the CNC, the digital camera, which is managed by a workstation. A scanning operation would not be able to identify the configuration and vulnerabilities associated with those. The lathe is connected to a server and communicates via Ethernet IP. There is a possibility to spoof this and have a man-in-the-middle attack. The lathe is being remotely monitored for performance using MT-Connect. This remote connection raises a third-party risk. Overall, there are many vulnerabilities in this configuration. In fact, the system can be attacked in at least 8 different ways. 5 of them are shown here. Hence, it is important to take a risk-based approach to cybersecurity and assess value of each strategy rather than starting with tools, technologies, or very narrow use cases. Cyber incidents faced by manufacturing companies over the last many years indicate that 70% of the risk come from a variety of human factors. An analysis of these incidents is allowing us to see how much and what types of risk can be addressed by each strategy as shown in the table. Clearly, environment-imposed vulnerability management offers the most risk reduction potential, about 45%. Segmentation, patch management, and intrusion detection can also help address good amount of risk. The next step is to identify one or more solutions that can address the most risk potential within each strategy category. We also must make sure the cost of the solution doesn't outweigh the value. This ResiliQ strategy matrix offers a framework to determine an optimal strategy and prioritize controls for implementation with the return on investment mindset. As you see, the first column identifies potential strategies. The second column highlights the risk reduction potential by each strategy category. The third column asks to input solution values. This can be a value derived from assessing each solution based on its effectiveness, cost efficiency, adaptability, and sustainability. You can also simply put down how much risk will be reduced by a given solution. The fourth column asks for cost of the solution. It is reasonable to use a 3 or 5 years total cost of ownership. Now you have an ability to see what provides you the best bang for your buck. I've also highlighted an example of optimal solution. As we can see, maturing cybersecurity via process excellence can deliver the most value. Usually, cross-functional operations managers are very good at leading such efforts and extracting the most value, more so than the people who are good at strategy development or implementation. The obvious next step or next question is how one should go about executing such an approach. A programmatic approach can yield the most optimal result. It brings everybody on the same page via cross-functional engagement and helps avoid the false sense of security that folks have. You can start with building a program structure. Make sure you have a cross-functional team engaged. Roles and accountabilities are well defined and understood by everyone. An operating mechanism is in place. Rewards and recognitions can help ensure engagement and promote desired behaviors. The second step, develop your optimal cybersecurity strategy or realign the one that you have using a framework like ResiliQ strategy matrix. Of course, this needs to be done in a full cooperation with your program team. Next, execute the approved and budgeted strategy for maturity. Your program steering committee will be critical in strategy and budget approval process. As a team, you must identify the maturity level that you desire and continue to measure your performance against the goal. So basic steps are organize, strategize, and execute, if you will. This approach works just as well for small and medium-sized businesses as it does for large multi-unit multinational corporations. Because a big portion of cybersecurity risk management comes from operational activities, you need engagement from each facility. So the program team can be at the facility level with coordination from the center. In a case of a small business, a facility level program team can report directly to the sponsor, who can be the CFO or a CEO. In large organizations, the steering committee should include functional leaders representing functional members of the program team. It is recommended that an influential operating leader be the executive sponsor of the program. The steering committee and the board can govern the program and support with critical decisions or budget. This may require 2 to 6 hours of monthly commitment from each cross-functional program team member in a steady state environment. One can start with more frequent program team meetings in the initial stages. Once the program is mature, the frequency can be reduced, if you will. Return on investment mindset is required to ensure the best value. This approach supports this mindset. As we saw, we can identify the risk reduction potential in agreement with the program team members in our strategy matrix. The knowledge of cost allows you to estimate return on security investment. The equation is just right here. A reasonable goal is to have a cost of less than 10 cents to reduce $1 of annual risk. The risk can be estimated as the total cost of a breach at a facility level, considering an organization has built an ability to isolate the facility in an event of a cyber incident. As we saw, cybersecurity of OT requires a different approach. An approach centered around heavy network-based strategies, centralization, and detection works well for the IT side. In fact, it delivers good cost synergies. The outcome isn't ideal when it's extended to the OT side. The operationally focused risk-based approach discussed here fits better for OT side. It complements the IT strategy as well. So in summary, again, consider the risk-based approach for OT cybersecurity. Presence of many unknown and uncontrolled variables is what makes cybersecurity challenging. So avoid having that false sense of security. Know that tools and technology-centered approach alone isn't sufficient to manage the risk. Building a culture of security goes a very long way to achieve maturity. And the risk-based, operationally focused programmatic approach is the most optimal answer. It balances among effectiveness, efficiency, adaptability, and sustainability. And as you can tell, the priorities for the IT sides are different than priorities for OT side. At OT side, safety, availability are more important than integrity and confidentiality. So approach has to mirror that. And as a result, you have to take operationally focused approach with people engaged on an operational level. So hope this course helps you identify your optimal OT cybersecurity strategy. Feel free to reach out with questions. We're available to answer them. Good luck with your journey. Thank you.